In this lecture, we'll study impulse response representation for LTI system and convolution sum. LTI system is the one which satisfies both linearity property and time invariant property. We know that a system is said to be linear if it satisfies the condition h(a1 x1 of n plus a2 x2 of n is equal to a1 h x1 of n plus a2 h x2 of n. Similarly, a system is said to be time invariant if it satisfied the condition x of n minus n naught is equal to y of n minus n naught. These two properties plays an important role to determine the behavior of the system. Using these two conditions, the behavior of the system to any input can be determined. Once we know the behavior due to one special input known as delta signal or delta function, or also known as impulse signal. Now let's consider the discrete time system. Consider discrete delta signal, that is delta of n as an input to the system. We know that suppose the system is having the operator h, suppose the input signal x of n is equal to delta signal, that is delta of n, then output of the system y of n can be represented as h of x of n, or it can be represented as h of, as x of n is equal to impulse signal delta of n, we will call it as h of n. So here the function h of n is known as impulse response of the system. Thus, if we give the impulse signal delta of n to the system, we will get the output as h of n. That h of n is known as impulse response of the system. So here h of n is known as impulse response of the system because it is response of the system when the input signal is impulse signal delta of n. Therefore, now I can write h of n is equal to h delta of n. Okay, we'll call it as equation number 1. Now we can say that when the input signal is a delta n, when it is applied to the system, it produces the output as h of n. Now let's see what output the system produces for some other inputs. Now consider the shifted delta function, that is delta of n minus n naught. Suppose now if the input, that is shifted input delta of n minus n naught is applied to the system, then the output of the system is, say, y of n is equal to h delta of n minus n naught is equal to h of n minus n naught. Here we got h of n minus n naught because we said that the system is time invariant. When the system is time invariant, the delay in the system, that is time shift in the input signal, produces time shift in the output signal. Therefore, h of n minus n naught is the response when the input signal is delta of n minus n naught. That is because system is time invariant. Now consider input signal to the system is say 3 delta of n. Now that is, this is the system. Now the input is 3 delta of n. Now the output of the system is h 3 delta of n, which is equal to 3h of n. So here we can say that just by knowing the behavior of the system for delta n, we can able to find the output of the system when 3 delta of n is applied to the system. Now consider the input signal is say x of n is equal to delta of n plus delta of n minus 1 plus delta of n minus 2. Now consider in next case we'll apply input to the system as delta of n, sum of signals delta of n minus 1 plus delta of n minus 2. Now the output of the system is, you will get it as h of n plus h of n minus 1 plus h of n minus 2. Similarly, now we'll consider another case. Similarly, now consider input to the system say x of n is equal to 2 delta of n plus 3 delta of n minus 1 plus 4 delta of n minus 2. To this system, the input x of n is applied, which is equal to 2 delta n plus 3 delta of n minus 1 plus 4 delta of n minus 2. In that case, it will produce the output, which is 2h of n plus 3h of n minus 1 plus 4h of n minus 2. Thus, by knowing the outputs of LTI system for impulse input delta of n, as we know for impulse input delta of n, we got the output as h of n. We have computed the outputs of LTI system when subjected to different inputs, which are scaled and shifted versions of. Now let's generate an arbitrary input, say x of n. The value of x of n at n equal to 0 is x of 0. In terms of impulse function, it can be denoted as x of 0 delta of n, because we know that delta of n value is 1 for n is equal to 0 and its value is 0 for n is not equal to 0. Therefore, when we take n is equal to 0, it will become delta of 0. Delta of 0 value is anyhow 1. Therefore, x of 0 into 1 is nothing but x of 0 itself. Similarly, x of n value at n equal to 1 can be represented as x of 1 delta of n minus 1, because we know that delta of n minus 1 value is equal to 1 for n is equal to 1 and its value is 0 for n is not equal to 1. Therefore, x of 1 delta of n minus 1 is nothing but x of 1 itself. Similarly, x of n at n equal to 2 is x of 2 delta of n minus 2. Delta of n minus 2 value is 1 for n equal to 2 and its value is 0 for n is not equal to 2. X of 1 at n equal to 3 can be represented as x of 3 delta of n minus 3. X of n at say n is equal to minus 1 can be represented as x of minus 1 delta of n plus 1. Similarly, x of n at n is equal to minus 2 represented as x of minus 2 delta of n plus 2. Thus, we can write the input signal x of n as x of n is equal to say x of minus 3 delta of n plus 3 plus x of minus 2 delta of n plus 2 plus x of minus 1 delta of n plus 1 plus x of n x of 0 delta of n plus x of 1 delta of n minus 1 plus x of 2 delta of n minus 2 plus and so on. We'll call it as equation A. So now in equation A, it is observed that the value of shifted delta function, that is delta of n minus 1, delta of n minus 2 and so on, is non-zero only at one time. Equation A can be written using some x of n is equal to summation k varies from minus infinity to infinity. Here x of k delta of n minus k. We'll call it as equation B. So now let a system having the operator is h, the input x of n is given, it produces the output y of n which is equal to h x of n. So similarly, now let h be the operator of the system. We'll apply this x of n to the system h. It produces the output y of n is equal to h summation k is equal to minus infinity to infinity x of k delta of n minus k. Now using linearity property again to interchange h and x of k in this equation, by using linearity property, now we'll interchange h and x of k. The equation y of n can be represented as y of n is equal to summation k varies from minus infinity to infinity x of k h delta of n minus k. We'll call it as equation C. Here equation C indicates that the system output is a weighted sum of the response of the system to time shifted impulses. So till now we have considered linearity property. As we know, system is time invariant also. Therefore we know that if H is the operator of the system, if input to the system is say delta of n minus k, then definitely the output will be H of delta of n minus k is equal to H of n minus k. Because the system is invariant, the shift in the impulse signal produces identical shift in the output signal. Therefore, for delta of n minus k, we'll get the output as H of n minus k. Now, replacing H delta of n minus k with H of n minus k, equation C can be rewritten as the output of an LTI system is given by a weighted sum of time-shifted impulse responses. The sum here is known as convolution sum and is denoted as y of n is equal to x of n convolved with h of n, which is equal to summation k varies from minus infinity to infinity x h of n minus k. So this is the output expression of LTI system, which is known as convolution sum. Thank you for watching.